Welcome to the Real Python Podcast. This is episode 267. What's a good way to enable or disable code paths without redeploying software? How can you use feature flags to toggle functionality for specific users of your application? Christopher Trudeau is back on the show this week, bringing another batch of PyCoder's weekly articles and projects. Christopher shares an article exploring the use of feature flags. The piece advises targeting specific users, storing schemas, and relying on well-worn code paths. He also discusses the danger of exponential growth of functionality tests as feature flags are added. We dig into a comparison of 6 popular Python visualization libraries. The article provides code examples with the respective visual output to contrast features and make selecting the optimal library for your work easier. We also share several other articles and projects from the Python community, including a news roundup, benchmarking MicroPython, simplifying IPs and networks in Python, a Scream cipher, and a browser-based graphical viewer for the output of Python's cProfile module. This episode is sponsored by InfluxData. Stuck with slow, time series data queries? It's not your code, it's your database. Traditional databases weren't built for timestamped data. InfluxDB was. Handle millions of data points per second, while competitors wait for dashboards to load. When you use the right tool for time series data, everything becomes faster, simpler, and more effective. Stop waiting. Start building at influxdata.com/realpython. All right, let's get started. The Real Python Podcast is a weekly conversation about using Python in the real world. My name is Christopher Bailey, your host. Each week, we feature interviews with experts in the community and discussions about the topics, articles, and courses found at realpython.com. After the podcast, join us and learn real-world Python skills with a community of experts at realpython.com. Hey, Christopher, welcome back.
Hey there.
So, we are here at the final release candidate, I think is what it was called.
I think those things are always expressed with hope, but yes, you're right. Yeah.
I mean, it's written on their thing there. It's finally, with magic wand emojis, the final 3.14 release candidate. So, yeah. But we got a whole bunch of news, obviously, that release, and some PEPs announcements, and then, our usual topics and projects this week. So ready to dig in?
Yeah, for sure.
Okay, great.
Like you mentioned, release candidate 3 for Python 3.14 has come out, and we're just weeks away from it going gold. Along the same lines, Django's got a release as well. Django 6 has gone alpha. Django's version numbers aren't semantic, so 6 doesn't mean backward incompatible changes with 5. In fact, for the most part, Django's been pretty stable for the last few years, and upgrading has been pretty smooth. That said, they are testing against fewer Python releases, so Django 6 will be 3.12 and forward. So if you're using something older, you're probably okay, but do note that they're not testing for it. Couple of bigger things in this release. The first one is template partial, so a way of making it easier to reuse small named fragments. And the second is their work on background tasks. There have been systems like Celery for doing tasks in the background with Django forever.
Yeah.
Now Django has codified an interface similar to how it does databases. So it defines a background task back end, and then there can be multiple implementations depending on your needs. So all of that's starting to happen. And I saw a release announcement of the first back end that is compliant as well. So there's a lot of work going on here. As is typical with .o releases of Django, the target for this is December, and there'll be one beta and hopefully one release candidate between now and then. All right, so let's talk PEPs.
Yay.
First is 782, titled Add PyBytesWriter C API, which has been marked final and is targeted for Python 3.15. At the moment, there are a couple of calls for dealing with the creation of Python bytes objects inside of the C extension space. Byte objects are meant to be immutable, but this interface actually allows you to muck with them, which makes them not immutable. And so what this PEP does is create a new API for creating and dealing with byte objects, which no longer allows this mucking about. If you don't write extensions, you don't need to think about this at all. Next is PEP 794, import name metadata, which is part of the standards track and has recently been accepted. This adds a way in the PyProject TOML file to relate a package's name with its import. So at the moment, there is no easy way for your IDE to know that import pill means pillow must be installed. This PEP essentially fixes that. And then finally, PEP 808, stable ABI for free-threaded builds, has been added. The ABI defines how compiled extensions get loaded so that they can be compiled once and used for different versions of Python. This PEP is about making the stable ABI available in free-threaded mode. That's the GIL-less thing. And as we're heading to that being the default eventually, hopefully, this will be necessary. And then the final bit of news is on the community side. The results from the Python Software Foundation board election have been announced. There are 2 new members and 2 who are rejoining. Congratulations to Abigail Dogby, Giannis Lytle, Sheena O'Connell, and Simon Willison.
Yeah.
I expect good things for Simon. I think he's an up-and-comer.
Yeah. All right. So I like to talk about visualization libraries, and I really liked this article. It's from Nguyen Tran, and it's from the CodeCut website. It's titled Top 6 Python Libraries for Visualization, Which One to Use, with a question mark. Often these types of articles are just sort of lists of features, but I feel there was a real strong focus here of how could I give advice to somebody else who's looking at trying to get into doing visualizations and which directions they should go depending on what direction they're coming from and what kind of background they have. And I thought it was really well put together. I've spoken about most of the libraries featured here. There's one that I haven't talked about yet that I've been interested in. And I think the guidance is really good. If you're looking at trying out something different or looking at maybe the library you're using doesn't quite fit certain stuff. So, and again, the number of libraries that are out there as far as visualizations go can really overwhelm someone who's just kind of getting started. I think the selection that is included is really good, and it starts with the TLDR sort of comparison chart. Columns for each of the libraries is included with rows for code complexity. Does it feature interactivity? What are the numbers of chart types and sort of variations that are available there? Is it a good tool for web integration? How well can you customize this thing? And then the last one, which is kind of an interesting one to think about, is what are the dependencies this thing needs? Like how sort of heavy is this library to use in your code? Along with that includes a quick sort of decision list. So if you're wanting to just like go through here again, TLDR, I'll not talk about that yet because there's a good one at the end also. An example would be choose matplotlib when creating publication quality static plots, need unlimited customization control, working on academic papers or research. So again, succinct advice on some of these libraries. And then the article digs into each one of them. A lot more detail for each of the libraries, starting with pros and then cons. And each section also includes code examples with the plots and charts generated for each of them. In fact, many of them show, especially if they're interactive or have animations or other things like that, it shows them as like little video GIFs to give you an idea of like what that looks like. She starts with matplotlib, which I think is a good choice to start with. It is probably the main one people in the Python world are familiar with. It actually is built into a lot of other libraries. It's the one definitely I was first introduced to when I started trying to do visualizations in Python. What are the pros? Well, it's very versatile. It is capable of generating a very wide range of graph types. It has animation capabilities, which is a unique thing in it. They show an animated line plot with like real-time data going across it, done as like a sine wave, giving an idea of that. And then something I hadn't seen, which is an interesting example, an animated bar chart race showing results as things change and the bar chart animating and going across it. The publication quality of the output of it. We focused on matplotlib pretty often on the show, and it has really detailed documentation. But to kind of get to that publication quality output, it kind of starts leaning toward the cons here. you're going to need some help because it gets really steep. There is kind of a bonus feature in there that's sort of a pro. Also, this idea of style sheets where you can take the work of somebody else and apply it to your own stuff, or again, kind of create presets of reusable stuff in these style sheets. Another advantage is that it's built into many other libraries, so your familiarity with it will help. It has a very steep learning curve is one of the cons. And then again, the extensive styling. To create like a very readable heat map in Matplotlib is going to require a lot of manual steps. Unlike other higher level libraries, which I'll talk about next, it doesn't automatically handle statistical computations or data preprocessing. So if you're going to do grouping, filtering, aggregation, statistical calculations, you're going to need to do all that before doing your plotting. It's quite capable, but requires lots of customization. So that's Matplotlib. Seaborn is the next one that is compared. The pros is that it's very reduced as far as the amount of code that you're going to need. It's really designed to be a higher level interface, and it really simplifies the plot creation. The first example is kind of comparing that heat map example, and it took about 4 lines of code in Seaborn to create something that's much more usable inside of Seaborn. It also excels at automatically performing the stuff that I just mentioned that the other one didn't. It has statistical computations and aggregations. It'll automatically compute like scatter plots and marginal histograms and correlation coefficients. So if you're looking for that sort of stuff, lots of good examples of code and output visualizations. It can do automatic pairwise relationships. So if you're comparing two things, which is really nice. Statistical summary with quartiles. Cons, it doesn't have as many levels of customization compared to Matplotlib. There's a limited plot collection, and it has no real interactivity or animation built into it. The next one I featured a few months ago, maybe it's longer than that, but it's called PyGal. It's a real lightweight Python library, and it generates scalable vector graphics, which I'm a fan of just because of that. You can put it on the web, and no matter what format you're looking at it, it's always going to look nice because it just scales to it the way like a PDF or other SVG type of tools do. So that is probably the biggest thing. This sort of perfect scaling is one of the biggest pros. It can be embedded directly into HTML without any kind of additional dependencies or image files. The files are going to be smaller than the typical sort of raster stuff that you'd have. PyGal's chart includes hover tooltips by default, and that's kind of nice because it then has an interactivity element with the SVGs there. You can explore data points, just sort of hovering over things without requiring additional JavaScript libraries or frameworks and stuff. It has some other key advantages in how it automatically will enhance common chart types with aesthetics that you might like, built-in interactivity. Nice examples included minimal dependencies, and fast loading is another pro. One of the cons is it's limited to 14 chart types. So again, kind of a small library there. I really like the examples, and the showing of the interactivity, I think, really helps get you an idea of like, okay, is this something I'm looking for? Plotly is the next one that's compared. Pros, it's easy to create really beautiful interactive plots. It lets you make complex plots, like things like maps or geographic distributions, and that's actually rather difficult to do in something like Matplotlib. It is probably going to be a good tool for you if you're in the business intelligence kind of field. It has enterprise-grade visualization features like the ability to drill down into charts and do real-time data updates as you add or subtract pieces that you want. Cross-filtering. I really like this about Plotly. These are the types of things that I wanted when I was working. I was building dashboards inside of this bank, and I was trying to give an idea of the ability to play with stuff. I think is something that I thought management would be really interested in, this idea that they could actually see what's going on underneath stuff and drill into things. And Plotly definitely excels there. Probably the biggest con is it's got very heavy dependencies. It has a substantial increase to your project size and deployment complexity. Altair is the next one, and that's the one I haven't experimented with. In fact, I feel like the name has changed to Vega Altair, VEGA Altair, and I didn't have time to do a deep research on the update or the change. It uses a grammar-based approach to graphics. I've talked about that before. There's a library that's popular in the Python world called Plot9, and we've talked about it on the show a little bit. It's based upon ggplot2 library, which is very, very popular in the R world. And it has this idea of this grammar of graphics where you're building plots sort of incrementally through layers. And so you're kind of like building the structure out. And so Altair follows that. It has a very simple visualization grammar. It's easy to do data transformations, aggregation, categorizing. In fact, there's a huge list with a link inside the article to all the data transformations that you can make inside of it. The ability to link plots, again, something that's really nice, where you can filter contents of one with your sort of interactivity, and it'll apply to the other one. Cons kind of lean toward the limited styling options, and an interesting limitation that some of these other libraries are really great about, again, doing aggregation and stuff like that for you. Here, you're going to need to do that beforehand, before bringing it into Altair. If you are exceeding over like 5,000 samples, it's going to have a problem with it. So handling larger data sets is going to require some extra steps on your part to manage. The last one that is compared is Bokeh. I did a course on this, and I truly need to update it, and I'm sorry. It's one of the first things I did when I joined RealPython. I really like this library. It's very, very flexible. It's very, very interactive, and it's truly designed for web browsers. In fact, one of the main outputs is like, do you want this to be HTML as an output, which is really nice. It's similar to Matplotlib in some of the ways that it's laid out, so maybe the learning curve would be a little less steep moving to that if you want to make a more interactive version of Matplotlib. It has some really nice examples here, again, showing off stuff, the code, the chart, the animations of the interactions. The ability to link plots is another thing that's really nice in this library. You can change one of the charts and just watch the updates happen across all the others. Really fine-grained control over web deployment. You can embed things inside of a website, create standalone HTML files, or you can create actual web applications with custom servers. So the big con is that the code can be rather verbose. So she provided, again, another summary. I'll just kind of go through her thoughts. Matplotlib, you would choose this for complete customization control and publication quality static plots. They require a little bit of work, though. Seaborn, you would probably select this for statistical analysis and elegant plots with minimal code. Plotly, used for interactive dashboards and web-ready visualizations. Altair, you would pick that if you want a declarative data exploration through the grammar of graphics. PyGal, opt for this if you want to do lightweight web integration and, again, simple SVG charts. Bokeh, you would go with this if you want complex web applications and flexible deployment options. So thanks again, Kuyen. I really like this comparison. It's very, very well thought out, and I really love that there's so many code examples kind of showing you, oh, okay, I get an idea of like what you mean by the amount of complexity inside of each of these.
Kyun writes good stuff. We link to her frequently in PyCoder, so a lot of good content from her. Just a quick note, Seaborn is actually built on top of Matplotlib. So if I remember correctly, there's a way of getting at the Matplotlib object once you've prepared it using Seaborn. So it allows you to like drill down and get at. So normally you're using Seaborn, you do that high level and you just ignore it and let it do its high level thing. But I think there's ways, if it doesn't provide something that Matplotlib does, I think there's ways of getting at the Matplot stuff underneath. So you can kind of use it as a quick way of doing Matplotlib graphs and then modifying them after if you need to.
And then drilling in if you need to.
Yeah. So I think it's basically like a wrapper with a bunch of style stuff like you mentioned before. So.
Let me guess. Your time series queries start fast, then begin to crawl as data grows. Traditional databases weren't built for timestamp data like metrics, events, or sensor readings. They crash on high-volume writes and time-based queries. InfluxDB was purpose-built for this. Millions of data points per second, automatic compression, sub-10 millisecond queries. It's like choosing the right Python data structure. Using a list when you need a set works, but it's not optimal. Time series data deserves a time series database. Visit influxdata.com/realpython. All right, what's your first one?
My first article this week is called Feature Flags in Depth, and it's by Raphael Gachenard. In case you're not familiar, a feature flag is an if block around a feature that you've added to your code. The idea being that by changing some configuration parameters, a feature can be turned on or off without redeploying your actual code. This is particularly useful in larger enterprise systems or software with a wide audience, as you might want a subset of your users to beta test something without wanting a whole version of the product just for them. So Raphael's article introduces you to the concept of feature flags. It starts out with a bit of taxonomy, beginning with the most basic kind of flag, a system-wide toggle, essentially on or off. But those are kind of limited in use. Ideally, what you want to be able to do is turn a feature on or off for specific users. And of course, if you've got a concept of a group or a team of users, then you probably want to attach the flags to that as well. Depending on the type of testing you're doing, you might want the flag to be enabled to a subset of users based on a percentage. That way you can do incremental rollouts. The challenge with this one is it needs to be stable across releases. So if I've got access to a feature in release 1, I better still have access to it in release 2. And you also may want to be able to override this. So if I got access and then it turns out I don't want it because you've broken something in my process, then you also need to be able to turn it off. So although the randomizer may have picked me, you may still want to be able to override that. So those are the most common requirements for feature flags. So how do you go about managing them? One approach is to use a feature flag as a service system. These are third-party flag management sites. The downside of these is each flag check means an API call. Raphael prefers to use a library instead, basically keeping the management local. If you're on Django, a good library out there is Django Waffle, which is my go-to and which we actually mentioned in episode 164. Raphael mentions it and then covers the basic database structure that it uses to manage flags. And as it's Django, it gets managed through the Django admin. Raphael goes on to mention some best practices for naming your feature flags. For example, new profile page 2023 is a decent name as it tells you what it is and when it came out. That way, if you create a new profile page again, say this year, because your product owner can't make up their mind, then you can differentiate. One of the challenges with flags is the combinatorics of testing them all. One flag means 2 states, 2 flags means 4, etc. So there isn't much you can do about this if you've got a lot going on. But once a feature has been rolled out to everybody, you can just permanently leave it on and not test its off state or remove it altogether. Another thing you might consider is trying to limit the flags to where the user interacts with the feature. So if you've got some front-end code that calls an API, the new part of the API doesn't necessarily have to be behind a flag. As long as it can't be called by the original non-flagged part of the system, you can essentially use the flag only for the UI. This can limit their impact in the testing phase and reduces some of those combinatorics. The article goes on to talk about how and when to remove the flags, the line between when to use a flag and when to branch your code, whether making them too easy to use is problematic for your project. And so all in all, a good introduction to the topic and well worth checking out.
All right. Well, my next one is kind of going back to electronics. It's titled Benchmarking MicroPython, and it's by Miguel Grinberg, who we've featured a few times on the show. He's been working with microcontrollers quite a bit lately, and he's actually developed a web framework that runs on these type of devices. It's called Microdot, and I'll include a link for it. He uses MicroPython for most of his experiments here. I have focused mostly on CircuitPython on the show, but the two are really similar. CircuitPython being more geared toward like ease of use and beginner-friendly libraries, where MicroPython might be a little more geared toward performance and low-level hardware control, which I think is partly why Miguel used it for his experiments in the Microdot framework. The Microdot framework, again, is like a kind of cool little web framework for working with these microcontrollers and connecting them and like having an API running on one of them. Miguel was presenting the Microdot framework at EuroPython 2025. He was asked from the audience about performance of MicroPython running on a microcontroller, and he hadn't really thought about it because it really was never an issue. These are small devices. The whole idea is that they are designed to be efficient, run on very low power, run sort of singular tasks, low memory, etc. They're not designed to be a full functioning computer. But he decided through this article to do an exploration of that. And he built actually not a singular benchmark, but actually several. He's not a fan of benchmarks. There's another link in the article about why. Quoting from his piece, benchmarking running code is actually quite difficult because the speed of execution isn't constant and can change dramatically from one moment to the next, so you can't think of results as absolute or universal. He went forward with this idea just to kind of get an idea, performed the benchmark across 4 different microcontrollers, and then included the framework laptop that he's currently writing the article in, he said, which is running Linux, and then a Raspberry Pi 4 Model B, which is, again, a true little computer. The first chart he has includes the models of these different microcontrollers and the RAM they have, and then comparing it to the computers. The lowest end one is the ESP8266, which has 64 kilobytes of RAM. The Raspberry Pi Pico W has 264 kilobytes, and the Raspberry Pi Pico 2W is 512K, and the ESP32S3 is also 512 kilobytes of RAM. Okay. The Raspberry Pi 4 Model B is 8 gigabytes of RAM, so quite a change. And then the framework laptop he has is actually 32 gigabytes. So if we're going to compare the laptop to the smallest microcontroller, it's 524,288 times the memory of the lowest unit. So quite the difference. He shares his benchmark first code, which is a Fibonacci sequence calculated to the 30th number. He's running time calculations inside of that. And in this particular case, he's using recursion as a first step. I've had Al Swigert on the show, and we discussed his book, The Recursive Book of Recursion. So if you'd like a little background on that and maybe some examples of that running in Python, episode 124 is all about it. In fact, his book is available free on inventwithpython.com. That's all one word, invent with Python. And you can learn a little more about it. But the idea here is that it's going to recursively run the same code again and again. And one of the funny things is the 2 lower memory units, the stacketh did overfloweth. So they weren't able to basically keep running. They just crashed. The other 2, the Pico 2W, which is one of the 512K units, ran the process in 16 seconds, and the ESP32S3 ran it in 30 seconds, which was surprising to Miguel, as the ESP32 is kind of known somewhat for its performance. And how did it compare to the computers? Well, the Raspberry Pi 4 took 0.6 seconds, and the laptop took only 0.08 seconds. Worlds of difference. Again, very different running with a complete computer and that kind of RAM. But he decided maybe I should refactor the benchmark so it can run on these smaller units. And so he removed the recursion, and he still was calculating the 30th Fibonacci number, but now it all ran way too fast. And so he changed it to run to the 50,000th instead and got a much better comparison. So how did they do? Okay, starting at the lowest end one was the ESP32 was 10 seconds. The Pico 2W was 24 seconds. The Pico just W is 31 seconds. And then the ESP8266 was 38 seconds. The computers were 0.02 for the laptop, and the Raspberry Pi 4 was 0.08. Kind of looking at the size of things, you can't really compare those performances between computers and those things. He was intrigued by the performance differences, but definitely the ESP32, which he had known would be performant, was really showing its strides against the Pico 2W. He decided, okay, let's do one more benchmark, and he wraps up with a bubble sorting one. And this one had the Pico 2W and the ESP32 kind of much closer. He provides his advice. If you're looking for recommendation, I would recommend either the Pico 2W or the ESP32 variants. Are both fine machines and would work well for any applications that need these kind of microcontrollers. They're a little more expensive. It's not a huge difference. We're talking like $10 or less for a lot of these devices, or €10. I'm not sure exactly how that compares right now with said tariffs and things. He leaves a final shout out to his library to keep in mind that Microdot, you can add a Flask or Fast API style web backend and host it inside the device itself as part of your project, which, again, very cool. And thanks, Miguel. I know you were interested in checking this article out, so do you have thoughts about it?
No, it did make me nostalgic. I do remember upgrading my first computer from 128 kilobytes to 256 kilobytes.
Yes.
It cost me hundreds of dollars, which would be the equivalent of thousands now. And the card was about 10 inches by 4 inches. So, yeah. Anyways.
Things have changed a lot.
Things have changed, yes.
Yeah, your phone has how much RAM now? Yeah, let alone storage, yeah. Oh my God. I remember the first hard drives being, 20 megabytes. That's like 20 floppy disks.
Yeah,
or more.
I worked at IBM for a little while, and a couple of the mainframe things were the size of a fridge, and they were still only like 50 megabytes. Yeah.
It's time to shine a spotlight on another Real Python video course. It uses concepts and theories in astrophysics to practice using data science tools in Python. And it's titled Exploring Astrophysics in Python with Pandas and Matplotlib. The video course was developed by my co-host, Christopher Trudeau, and he'll be your host, taking you through introductory astrophysics topics, working with data frames and pandas, writing code that uses scientific units, and visualizing information with Matplotlib. This course uses 3 problems, often covered in introductory astrophysics courses. Along the way, you'll learn some astronomy and how to use a variety of data science libraries like NumPy, Matplotlib, Pandas, and Pint. Real Python video courses are broken into easily consumable sections. When where needed, include code examples for the techniques shown. All lessons have a transcript, including closed captions. Check out the video course. You can find a link in the show notes, or you can find it using the search tool on realpython.com. What's your next one you got?
I've got an article called Hidden Python Powers Master IPs, Networks, and Subnets Efficiently, and it's by හැ$ษิan. This one kind of reminds me about Python's claim of being batteries included. Mo does a lot of network engineer work, and Python's a pretty decent language for scripting this kind of stuff. Let me give a little bit of background first for anyone who doesn't spend a lot of time in the networking space. When you type a URL into a browser, that hostname part corresponds to a number called an IP address. Your computer does a lookup of the hostname to get the IP address, then uses that IP address to connect to the remote computer. That lookup process is done through a DNS server. This is kind of like using your contacts app in your phone. You look someone up by name, and it translates that into their phone number so that you can text with them. See, I can be modern. I didn't mention phone books or phone calls in that analogy at all. So, yes, up to date. Anyways, there are actually 2 common standards for IP addresses on the net, the first being IP version 4 and the second being IP version 6. Nobody liked 5 and it disappeared quickly. The article concentrates on version 4, but most of what Mo talks about applies to both. A version 4 IP address consists of 4 numbers separated by a dot. So, for example, Google hosts a DNS server that does those kinds of lookups that I was talking about earlier at 8.8.8.8, which is handy to remember in case your DNS server falls over because you can point at them. Each of the 4 segments ranges from 0 to 255, and although there are some restrictions on what certain numbers mean. So, for example, the address 127.0.0.1 is your own machine, and so that's kind of hard-coded. All right, so on to the Python standard library. It has a module named IP address, which allows you to start with a string version of an IP and get back an object. And then once you've got the object, you can do things with it. For example, if you need to deal with a range of addresses, the IP address object supports addition. Whereas if you had dot notation, you'd have to splice the string and do that yourself. So +1 means get me the next address, which is nice and handy. When dealing with networking equipment like firewalls, which Mo often does, you often need to create rules that apply to ranges of addresses. So, for example, I want all the addresses on my network to be able to get to a certain machine, but addresses not in my network should be blocked. IP version 4 supports a way of specifying such a range. I'm not going to get into the details, but you start with a base address and then provide a bit mask specifying which parts of the address can change and still be part of the range. The Python library supports both applying a mask as well as using what is known as CIDR format to get the same result. If you've ever seen a network range specified with like /24 on the end, that's a CIDR format. The Python library has a class for these ranges called IPv4network. And once you've got a network object, you can use the in operator to see if an address is within it. And you can also iterate over the network object to get all the possible addresses inside of it. Mo's article goes on to show you how to deal with subnets, how to combine address and network objects into interfaces, how to inspect various properties of the address, like is it part of the private network range or not, and more. So if you're a network engineer and you're new to Python, you should check this out because it'll help you solve problems. Or if you're a Pythonista who wants to learn a bit more about networks, this is a good place to start as well.
Well, I think that takes us pretty quickly into projects. And my project is kind of more of a puzzle problem, which I think is kind of funny. A common puzzle problem that would come up when you're learning coding is creating a cipher or possibly a Caesar cipher with a rotation of cipher letters. There's also something that's a little more complex that I haven't played with called a stream cipher. It has a symmetric key cipher where the plain text digits are combined with a pseudo-random cipher digit stream. You can look it up. But this is a real quick project for a Scream cipher. Seth Larson, who is the security developer in residence for the Python Software Foundation, and also a fellow Pikmin enthusiast like myself, he writes on his blog, "Today I learned there are more Latin capital letter A Unicode characters than there are letters in the English alphabet. You know what that means? It's time to scream." So he shares his code for the cipher, which basically is, again, combining all the different letters in the English language alphabet, capital letters, and converting them into various versions of the Latin capital letter A Unicode characters. And so the ciphers end up being, again, all these accented capital A's, and it looks quite a bit like a screen when you print it out. So pretty fun. Again, a quick project if you're interested in ciphers or puzzles. Check it out. What's your project?
So pull up a chair. It's story time. I'm in the process of rewriting some code of mine to go from a library that isn't maintained very well anymore to one that is. My original code mucks around with lists of strings a lot, creating tens of thousands of permutations, and each of the permutations then gets tokenized and processed. The new library that I'm using does some of this tokenizing for me, which sounds like a good thing, but that means I'm no longer able to permute the strings directly, but I'm using the objects in the library instead. The result is, instead of having a long list of strings, I have a long list of trees. My first approach was rather naive, and although it worked, it was taking a long time to run. One of my data sets was taking several seconds for the program to start, something that was nearly instantaneous before. So, like a good little programmer, I pulled out Python's cProfile, which generates performance information for each call in my code. I don't run into performance problems a lot in Python just due to the nature of the kind of code I write. So although I used to live and breathe profilers in other languages, I've only used cProfile a half dozen times or so. When you use cProfile, what you get back is a long list of every call made in your code and its runtime. Usually for me, I run it. It points out which of my functions is bogging things down, and then I go in and attempt to optimize. This time, though, I had a different problem. Due to the nature of the code, the thing that was taking up the most time was calls to Python's deep copy. And obviously, that's not something that I can make any difference with. This was happening in a bunch of different places, so it was hard to tell which of my calls were causing the problem. And thank you for your patience. The solution I found is my project this week, which is called SnakeViz, and it's by Matt Davis. He goes by Jiffy Club on GitHub. So this tool is a visualizer for profile data. What cProfile gives you is just a list, whereas SnakeViz gives you an interactive hierarchical representation of your code, with larger blocks being things that took longer. To use it, you call the cProfile module from the command line and output the results to a perf file. Then run SnakeViz on the output, and it launches a web server. You visit the server with your browser, or it'll do it automatically for you if you like. And then inside your browser, you get the visualization. There are two different visualizations available. The first is called Icicle and consists of a series of blocks, each representing a call. Your first line is the whole program. The line under it is then blocks that are proportional to their calling time. So say one of your functions is taking up a lot of time, that function will be a longer block, and then under that will be the timings of the parts of that function. You can click on any of these to redo the diagram rooted at that block, essentially zooming in to see what's going on. The other visualization is called a sunburst, and it's a similar idea but uses a series of arcs, so it's a pie charty kind of thing instead. When you mouse over any section, you get more details about the call, including things like the cumulative time and where the file is and the directory and all that kind of good stuff. There are also controls for the depth of the diagram, as well as how soon little small segments get cut, allowing you to adjust parts of the diagram that you want to focus on. So Matt, if you're listening, thanks. This library helped me figure out exactly what my problem was. The good news for me, by adding a simple if statement, I cut the processing time in half. The bad news for me was to get rid of the other 3 seconds. I had to do a lot of major surgery. So there was 3 days of coding I won't get back. You should always profile before you optimize, as your gut on what is and isn't expensive is probably wrong. If you do find yourself having to profile, SnakeViz is a pretty handy tool to keep around.
So which of the chart styles worked the best for you?
I only used the Icicle. It looked similar to tools that I have used in the past, so I didn't even play with the other one. For me, essentially they were like, the call to deep copy was taking up like 6.5 of the 7 seconds. So like it was just this massive block. And then below, so it really, like, it was just essentially like, it was almost a straight up and down tower of the deep copy from this function, from this function, from this function. So it just was a little layer cake. And so it made it very, very easy to see that.
That's really nice. Yeah. I've used tools like this for like files to like, just look at your file system. Like, what is eating up all my storage? Yeah. Awesome. Well, thanks for bringing all these articles and news and projects this week again, Chris.
Cheers. Always fun to be here.
All right. And don't forget, if you're working with any timestamp data in your Python projects, you owe it to yourself to try the right tool for the job. InfluxDB makes time series data effortless. Whether you're building analytics dashboards, monitoring applications, or tracking performance metrics, join millions of developers who've already made the switch. Get started today at influxdata.com/realpython and see the difference the right database makes. I want to thank Christopher Trudeau for coming on the show again. And I want to thank you for listening to the Real Python podcast. Make sure that you click that follow button in your podcast player. And if you see a subscribe button somewhere, remember that the Real Python podcast is free. If you like the show, please leave us a review. You can find show notes with links to all the topics we spoke about inside your podcast player or at realpython.com/podcast. And while you're there, you can leave us a question or a topic idea. I've been your host, Christopher Bailey, and I look forward to talking to you soon.